Hello AP Statistics students. In this video, we're going to first take a look at the idea of independence between two events. So we're going to test whether two events are independent of each other. We started that a little bit in class, I think, but didn't get a chance to finish it. Next, we're going to take a look at two rules for finding the intersection probabilities. So something like the probability of A and B. So there's going to be a general rule that always works, and then a simplified form that only works for those independent events that we'll have just learned about. And then one tool that does this really well for us is the tree diagram. It's really easy, and it works well for finding probabilities. So first off, independence. What is it? So independent events is where knowing if one event has occurred or not does not change the probability of the other event occurring. All right, so two events are independent if knowing whether or not one event has occurred changes or does not change, has occurred, does not change. I take that one out right there. There we go. Does not change the probability of the other event occurring. So, quick two examples of how this can go. First, the Facebook Instagram example. So we pick a random person. What is the probability that this person uses Instagram? All right, right here we've got, if you remember that from that example, 28% used Instagram. All right, so we got that in our minds. Next, now I tell you that this person uses Facebook. Does your opinion or idea of the probability in the first one change? Now that you know this person uses Facebook, do you believe there's a higher or lower or the same chance that they use Instagram now? If you think the chance is the same, like, no, they could use Instagram, they might not, I think the probability is the same, then the two events are independent. But if you think that knowing that they use Facebook now either increases or decreases their chance of using Instagram, then the two events are not independent. All right, so we can test this pretty easily with these statistics. So we know the probability of using Instagram is equal to 28%. And we're going to compare that with the probability of using Instagram given that a person uses Facebook. Does knowing they use Facebook change that probability? All right, and so we did this today. That is the probability of Instagram and Facebook divided by the probability of Facebook. So what does that give us there? So we have the top one. They gave us that. That is 25% over. The probability of Facebook is 68%. So that gives us a total of 25 divided by 68 is 36.7%. Well, look, that is a pretty big change. Now, I'm not looking for them to be exact, 28 point, whatever. But if there's a decent change, then they are not independent. One of them is associated with the other. Knowing that somebody uses Facebook changes the probability that they might use Instagram. So these two events are not independent. All right, let's do one more of those here. So now the pierced ear and gender example. So we have people, male and female, that either have pierced ears or don't. So we pick a random person. What is the probability that this person has an ear piercing? So the probability of a pierced ear, let's go PE for pierced ear, is equal to, we can actually use our table for that. It is going to be 103 out of 178. So 103 divided by 178 is 58%, roughly. So there's a 58% chance a random person has an ear piercing. Now, I tell you this person is female. Do you think that percent is going to change? I'm guessing your answer is yes there. All right, you think there's now a higher percentage or a higher probability that they're going to have an ear piercing. Well, that means these two events are not independent. Knowing one changes my opinion of the other. Okay? Now, I can verify this by comparing that with the probability of getting an ear piercing, PE, given that this person is female. What is that probability? Well, we can do that on the table pretty easily, can't we? So the probability just of the females right here, because it's given that it's female, and we're looking at, yes, that they have an ear piercing. So 84 out of 88, which is quite large. 84 divided by 88 is 95%. So that definitely was a big jump. So these two events, having an ear pierced and gender, are not independent. There is some kind of association here. Okay? So, what is the general equation here for independence? We first take the probability of an event, the first one, and we compare that to the probability of that same event given something else has occurred. And if they are equal, then they are independent because nothing changed. All right. The given B didn't change the probability if they are equal. Now, the examples we had, they never were equal, and so they are not independent. But that wasn't the only way. It actually, you could do a different way here. You could also do the probability of A given not B. All right, the other half of B. So here we did, in this case, ear piercings given that somebody is female. We didn't have to choose female. We could have chosen male. Okay, that's not female. It doesn't matter which one you choose. If one of them is not independent, you should be able to see that same relationship if you use the other part of that variable. In terms of doing things backwards, we could have also switched A and B. So the probability of B needs to equal the probability of B given A. So in our previous experiment, we could have flip-flopped these. What is the probability somebody is female given that they have a pierced ear? This relationship will also show up if you flip-flop the A and the B. In this case, gender and ear piercing. You will still see that that probability changes, or if it doesn't change, then they are independent. And then similarly, you can then flip-flop which one is the given, or sorry, you can give the not equivalent. B given not A. That is also perfectly fine. So again, remember, if all these probabilities are equal, then the two variables are independent. If they are not equal, then they are not independent. It means if they're not independent, there is some association of some kind between it. We can't say one causes the other, certainly no, but there is some kind of association going on. All right, so here is a good example. I'd recommend that you pause the video here, read this, try it out yourself, and then I will get the answer up once you are done. So pause the video, do it. All right, here are the two ways I solved this one. So the first example, I did the probability that you are a male in this study. All right, so that became 46%. And then I thought, all right, does that change if I now know you are left-handed? So that would be this one right here. The probability of male given you are left-handed, and I got 70%. Those two are very different. That means these two variables are not independent. Okay. All right, next. The other way you could have done it, I picked another one. There's many different combinations here. Hopefully you saw that you could do this. I chose first the probability that you are left. There's a 10% chance that you are left-handed in this whole study. That is simply the 10 over 100. And I did the probability that you are left-handed given that you are not male, so female. Looking at this column, and then the left-handers are 3, so 3 out of 54 gives me 5%. I compare those two, also very different. All right, one is double the size of the other, from 5% to 10%. Different numbers, same conclusion, not independent. All right, now we're going to take a look at, actually, I think I'm going to end this video right there.